In the first videos, we talked a lot about the Scanimate itself and played with some of the knobs and sort of pre-built functions. But to go really into depth in animation with the Scanimate, you have to kind of understand a lot about analog electronics. Well, not a lot, but enough. And so I'm going to try to simplify that as much as possible and talk a little bit about various elements you use when you build animations, and this is good electronic information that applies to a number of things. So first of all, in terms of notation, the animators did have a notebook that they kept where they recorded the circuits that made certain kinds of animation, and they used a form of notation. So for example, if you see a circle, that means it's an oscillator. Generally, they would draw like a sine wave or a triangle wave, depending upon which function you had set for that oscillator. Then if there's something that controls the amplitude of that wave that's coming out, that would be drawn in from the top, sometimes from the left. But generally then the outputs go either to the right or to the bottom. So you can build a big tree of these various elements. So that would be an oscillator, and if there's some kind of special notation that you need to know when you program it for a particular animation, you would write that in the circle. All right. Probably where we should have started is a much simpler. This is the symbol for a resistor, and the Scanimate is full of what are called variable resistors. So that basically means that's a pot. And I thought what I'd do is show you, this is a very large version of a pot. The ones in the Scanimate are a lot smaller than this, but I've got a knob on it here. You see it has 3 terminals, and the 3 terminals, if you look at the back of it, there's a little wire band that goes around this side. This is hooked to one end of it, this is hooked to the other, and then the middle is hooked to this slider. So as you turn the knob, it slides this resistance value up and down. And that's really all that's going on in an analog pot. And the Scanimate uses these in a couple of different ways. One way, this would be hooked to ground, and this would have a signal. So let's draw a sine wave there. And then as we turn this pot up and down, the amplitude of the sine wave coming out here, there would be a small amplitude, and as we turn the pot up more, we would have more amplitude, more amplitude. So we can control the gain or the amplitude of the wave coming out of this oscillator with this pot. That's called a gain pot. All right, now there's another kind which is the same variable resistor, and it's got a slider on it, but this is called a bias pot. And what that means is, and there are different ways of doing this. In the Scanimate, most of the bias pots are connected to ground at the bottom and to either +5 or +10 volts at the top. So all that means is that you get a variable voltage. So if this is at the 50% point, we're going to get 2.5 volts. So remember, all of these things on the Scanimate are controlled by voltage. So we've got to be able to adjust a bias. All right. The third element that we need to talk about is, in the Scanimate terminology, just a simple summing amplifier. Now, in actual electronics, that's called an op amp, and there's a resistor here and a resistor here. This is called the inverting input and the non-inverting input. So in a regular electronics world, that's an amplifier. If these are the same value, if you put a sine wave in here, you'll get the same thing out here, but it'll be inverted. Okay, now in the Scanimate world, we've kind of simplified that. That resistor is there, but you don't need to worry about it. And this is here, but you don't need to worry about it. So what they've done in the Scanimate is give you 3 different inputs and either 1 or 2 outputs, depending on where you patch to get to that amplifier. So what that means is, if you put a 1 volt sine wave in here, it'll come out as a 1 volt sine wave, but inverted at the output. Well, what if you need more gain than that? Well, you use the patch cords and connect that input to 2, or that sine wave to 2 of the inputs. Then all of a sudden this 1 volt sine wave becomes a 2 volt inverted sine wave. Okay, so you can get up to a factor of a gain of ×3 using this technique. Okay, so that's basically what in Scanimate terminology is called a summing amplifier, and the animators always drew a summing amp much simpler than that. They just drew a triangle with 3 inputs and 1 output. So if you need a gain of 3, you hook something to all 3 inputs. So that keeps it simple. You don't really have to understand a lot of the underlying circuitry. It just works for you. All right. Now then, the next element that we run into is called a ramp generator, and in the electronics world, that works by having a capacitor across this input. So the way it works is, if you suddenly change this voltage, the amplifier tries to make its output move in the opposite direction, because that's the inverting input, but this capacitor is charged up and it doesn't let it. So it tries to move, but then the capacitor begins to accumulate a charge, the difference between here and here, and so as a result, in time, you don't get a sine wave or something like that. What you get is what's called a ramp. And a ramp usually starts at 0 and goes to 10 volts. Of course, if it's been through a summing amp, it'll be inverted, so it'll go from 0 to -10 volts. Okay, now there are several special ramp generators that the Scanimate uses that have to do with creating a raster. We'll talk about that in just a moment. Okay, so that's a ramp generator, and most often the ramp generator is started by an external event. So if this switch is closed, the ramp gets held at 0. As soon as the switch opens, the capacitor starts to charge and the ramp takes off in a linear fashion, and as a result, you get a voltage waveform output that will move at a certain speed. And so then you can change that speed by changing that resistor or by changing the voltage here. So a ramp generator can be used to generate a horizontal sweep or a vertical sweep, and a raster can also be used to do an animation. And a lot of times in an animation, you don't want just a straight line move between keyframes. So a lot of times they use a sine wave function in the ramp generator, which gives it a slow in and then a slow out. I hope you can see this all right. Okay, so that's a ramp generator. Now then the final, well, not really the final element, but the next one we need to talk about is called a multiplier. Multipliers actually automatically have an amplifier on the output, but we don't really have to draw that. We just, in my notation, I always assume an output is to the right or to the bottom, an input's to the top or the left. Okay, what happens in an amplifier is that this voltage, and there's usually two inputs to a multiplier, the two voltages literally get multiplied together and divided by 10. That's one of the little things that's kind of inconvenient. But obviously, if you had 10 volts and 10 volts, you can't make 100 volts because we're dealing with things within a very limited range here. So 10 volts plus 10 volts and plus 10 volts would give you plus 10 volts out of your multiplier. Okay, so if we change this to 5, then we're only going to get 5 volts over here. All right, what's it good for? Well, the best thing that you can use a multiplier for, let's take an oscillator that's making a sine wave and put that to one of the inputs. And then instead of plus 5, let's take that to a ramp. In this case, an animation ramp that's going to go from 0 to plus 10 volts in 5 seconds. All right. So what's going to happen is when this ramp is at 0, when it's reset, anything times 0 is still 0. So you get nothing out of here. You turn the ramp loose and it goes from 0 to 10 volts. And what's going to happen is that the amplitude of this oscillator is going to get turned on by this function. So it's going to start like that. It's going to go to maybe plus and minus 5. Then it'll go to plus and minus 10. So the multiplier is used to turn on and off another analog signal with a voltage. All right, so those are the basic elements that we use in making an animation. Everything other than that is just routing. One of the things we do in the Scanimate is route something to what's called the cherry switcher, and I'll talk about that when we get back over to the machine. But at this point, I just wanted to talk about a little bit of the electronics. We were going to talk about raster too. Digital TV, it's all different now. It's all ones and zeros. But back in the analog days, the way television worked is you had a very fast ramp that went from 0 to, say, plus 10. And what that did is that it deflected the CRT's beam from the left side of the screen to the right side of the screen. Then it blanked off and did what was called a retrace. So if you look at the waveform for that, it looks like that. So this would be when the beam's at the left-hand side of the screen. This would be halfway, and this would be at the right-hand side of the screen. And then it resets and goes back. So if you only had a horizontal ramp going to the X of the CRT, you would get a line. But where it gets interesting is then if you make another ramp that's much, much slower. So like at regular TV rates, this runs at 15,750 hertz. 15,750 times a second. That sawtooth makes a line. Okay, well then if you take another sawtooth that's much slower that runs at 60 hertz, then what's going to happen is by the time it retraces and gets ready to draw the next line, it's moved down a little bit. And then the next line, it's moved down a little bit, and the next line down, and so forth. Now the magic thing about video is that that's called a field. When it gets to the bottom of the frame, it's in regular NTSC video, it's done 262.5 lines. And so then the next time up, because of a trick in timing they do, it actually comes back and draws another line in between the first one and the second one, and then between the second one and the third one. I'm not drawing these lines very good, but so the result is you have two fields that are interlaced. And so it will refresh the picture on the screen 60 times a second, but with only half as much information. And that's why if you look at a frozen frame of video, sometimes you'll see what looks like two different pictures with slightly different timing. And that's where the two fields are frozen. They're not really meant to be shown that way, because always one comes after the other, and then another one comes after that, and another one comes after that. And your eye blends all that together, so it's like you've got a 60 frame per second video. Only you're only using half as much of the bandwidth that it takes to send that. With HD TV, that's all out the window, and they've got progressive and interlaced and all these different formats, but we don't need to talk about that just yet. So by the time you have a standard NTSC picture, you've got 525 lines. Actually, there are only 480 something that are visible, and that's called a raster. Okay, in the Scanimate, you've got a horizontal sawtooth and a vertical sawtooth. So if you feed the horizontal one to the x-axis of the CRT and the slow one to the y-axis of the CRT, you get what looks like a square or 3x4 box. So then if you use the intensity of a video signal to turn that beam on and off, then you don't have just a square anymore. You've got the letter A or a picture of somebody's face or any number of things. So that's sort of the beginning. Now, how does all this come together? I'll just give you a real quick example, and then we're probably over for time on this one, and we'll get back to the machine. But let's say you've got the horizontal ramp, which a lot of times in the notation was just drawn as HR. So the horizontal ramp, if we feed that to a multiplier, and then if we feed the vertical ramp to the other input, then if we also feed the vertical ramp to the Y deflection of the CRT, and this goes to the X deflection of the CRT, what's going to happen? Well, at the beginning, when the vertical ramp's almost nothing, we'll get very little horizontal ramp coming out of this multiplier. So what that means is that at the top of the picture, we've made that raster almost go to a dot. Whereas at the bottom of the picture, where the vertical ramp is bigger, we're allowing the horizontal ramp to be bigger. So the scan lines near the bottom of the picture are suddenly going to be bigger, and the ones at the top of the picture are going to be smaller. So we'll look at that in the next video, and I hope I haven't run over and confused everybody, but these are important analog concepts to kind of grasp, because next what we're going to do is patch a bunch of these together and do things like this to raster. I hope you enjoy it. Send your comments, and I'll see you next time around.